Hello everyone, thank you for being here today, and I'm going today to present to you the work I did during my PhD thesis at the Laboratoire d'Optique Appliquée in Palaiseau, entitled Generation of Attosecond Radiation and Particle Beams from Liquid Lift Target in the Relativistic Lambda-cubed Regime. But first, let me introduce what is an attosecond radiation and why do we need such short bursts of light to do ultrafast science. Well, we need short bursts of light to decompose the movement of phenomena in nature. And usually the humans go by the second, but if you go down to 1 millisecond, 10 to minus 3 seconds, you can decompose the movement of a running horse or of a shooting bullets thanks to ultrafast camera. Then if you go down even more to 1 nanosecond, 10 to minus 9 seconds, you can study the electrodynamics process in the microprocessors thanks to fast oscilloscope. And with the advent of ultrafast lasers, you can go down to 1 picosecond and 1 femtosecond, respectively 10 to minus 12, 10 to minus 15 seconds, to decompose the movement of atoms and molecules. And if you can reach the attosecond radiation, so 10 to minus 18 seconds, you can then decompose the motion of an electron around the nucleus. So the generation and the usage of attosecond radiation has been awarded a Nobel Prize quite recently in 2023, and is mostly based on the gas high harmonic generation. So you focus an intense laser of 10 to the 14, 10 to the 15 watt per centimeter square in a gas jet. Doing so, you will excite electrons, and they will recombine every half cycle with their parent ion and generate an XUV burst. So every half cycle, you will have an XUV burst, and that corresponds to an attosecond pulse train in the time domain, which is equivalent to a spectrum of harmonics in the spectral domain. So this is a rather mature technology, known now for many years, and has been used in many applications from electron microscopy to electron dynamics in amino acids. So thanks to gas harmonics, you have a continuous, coherent, broadband XUV source, but not intense enough. So if you look at the laser intensities available, gas harmonic usually happens from 10 to 12, 10 to 15 watt per centimeter square in the realm of nonlinear optics. So you use high-frequency dipoles mediated by tunnel ionization of electron and its recombination to generate gas harmonics. But we know nowadays that laser intensity keep increasing, so why not use more intense laser? Well, when you go above 10 to the 15 watt per centimeter square, you have the plasma breakdown. So you start to create a plasma, so you create a soup of ion and free electrons, and this process doesn't occur anymore. But what if we still want to use more intense laser? Well, So gas harmonics then have an inherent limitation based on the incident intensity of the laser of 10 to the 15, and this mechanism is inherently limited in the conversion efficiency from the laser energy to the XUV energy at 10 to minus 6, 10 to minus 4 at best. But what if we use more intense laser? Well, you enter the plasma optics realm, and if you can go above 10 to the 18 watt per centimeter square, then you are in the relativistic optics, where instead of high frequency dipoles, you use collective source motion mediated by electron acceleration close to the light of speed, to the speed of light, relativistic velocities, to generate relativistic harmonic generation. And this is what I'm going to talk about in the first part of this presentation. Then I will talk about the laser that I used during my PhD to reach relativistic intensities. Then I will talk about what my group did for the past 10 years, including when I joined, so generating relativistic harmonic from solid target, the result and the limitation. I will then go with the core subject of my PhD, which is liquid lift targets. So why do we want to use a liquid target instead of a solid target for relativistic harmonic generation? I will talk about the design, the installation, and the challenges that I faced during my PhD, with, of course, the mechanical characterization of the target to see if it's as good or better than the solid target. Then I will talk about the experimental results, with first installing the liquid target instead of the solid target to faithfully reproduce the result from the solid target to see if it was worth it to replace, and explore the new capabilities offered by the liquid target afterwards. I will finally conclude on my work and open some perspective on the future. So first, what is relativistic harmonic generation? So you start from a solid target, you come in with a weak pump pulse of 10 to the 14, 10 to the 15 watt per centimeter square, focus at an oblique incidence on the surface of the solid target. After some time, allowing for the plasma expansion, so to have the right plasma gradient scale length, you come in with a driving femtosecond laser with an intensity, relativistic intensity of 10 to the 18, 10 to the 19 watt per centimeter square and more, that you focus down on the surface of this overdone plasma. And in the relativistic regime, the plasma surface itself acts as a mirror, but oscillating at relativistic velocities, which means that during the interaction, the plasma wave will periodically stretch and compress the laser pulse in time, and provided that you control well the condition of interaction, meaning that you control well the expansion of the plasma, you have high harmonics of the fundamental laser that are generated in the specular direction that correspond to attosecond pulse train in the time domain. So those harmonics, those attosecond pulse have been shown to be Fourier transform limited with a higher conversion efficiency than gas harmonics that can reach the percent level. Of course, since the harmonics come from the electron dynamic, you have also simultaneously an emission of relativistic electron bunches around the specular direction. And if we dive a bit into the electron dynamic within the plasma responsible for the harmonic generation, well, here on the left, you can see a representation of one optical cycle, so one oscillation of the electric field. Beneath, you have a peak simulation of the electron density within the plasma. And on the right, you can see a simulated video of the plasma wave creating XUV burst as the laser arrives. So with the first half cycle, you have a push effect, which means that you will push the electron within the plasma, creating an electron peak density of nanoscale electron bunch. And with the second half cycle, you will have a pull mechanism where the electromagnetic forces this time add up and you will rip electron out of the plasma. And every time you rip electron out of the plasma, you will generate an XUV burst. So this happens every cycle, and the oscillatory motion induces a phase modulation of the reflected field. So this is the so-called push-pull effect, push-pull mechanism. Experimentally, this has been shown to be optimal at a certain plasma gradient scale length of a tenth of the laser wavelength, and the harmonics are usually generated around the critical surface. And the goal in our group is to try to isolate one of the bursts that you see from the video over here. But to do this, we need relativistic intensity. So to do this, we use a laser in the lambda-cubed regime. So we use a 1 terawatt laser system, few millijoule, near single cycle, focus down on the surface of the target to a focal spot size comparable to the laser wavelength, which means that the focal volume is comprised within spatially lambda square and temporally lambda as well. So you have lambda cube. That way we need less peak power, but we can still drive the plasma mirror in the relativistic regime at a kilohertz repetition rate, which means that we have access to incredible shot-to-shot stability, statistical study, and since we are near single cycle, we have access to the control of the carrier envelope phase, which means that we can temporarily gate the interaction to generate intense isolated attosecond pulse that correspond to an XUV continuum in the spectral domain. Now we'll talk about the laser that I used during my PhD. I used the Salnoir 2 laser, which is a homemade double TISAF CPA architecture laser with a post-compression stage to go down to a near single cycle that can deliver on target pulses of 2.5 millijoule, 3.5 femto at 1 kilohertz. With here beneath, you can see the three main characteristics of our laser. The first one being the high temporal contrast ratio, because you need a clean interaction between the expanding plasma and the main pulse. The control of our CEP is such that we have a waveform jitter of only 100 attoseconds, and we have an amazing beam pointing stability of less than 0.2 microrad with an energy stability of 0.5% RMS. So what did we do with this laser for the past 10 years? Well, we generated relativistic harmonics from solid target. So here you have a view from the top of the interaction chamber, what it used to be with the solid target. You have the pre-pulse coming in, so the pump pulse, which is 100 microjoule, 200 femto, focused down on the surface of a solid target to a focal spot size of 10 micron. Then you have the main pulse, so 2.5 millijoule, 3.5 femtosecond, focused down on the surface of the solid target, overlap spatially and temporally with the pre-pulse to a focal spot size of 1.7 micron. In the specular direction, you have the high harmonic generation, characterized with a homemade XUV spectrometer. And here, on the middle left, you can see a typical angularly resolved spectrum of the harmonics with on top the spatial integrated trace. And since we are also interested in the dynamic of the relativistic electron, but we don't want to block the harmonics, we put a scintillating screen that I will call later on in the presentation LANX to image the beam profile of the electron, and this is what you can see on the bottom left, which is a typical angularly resolved beam profile of the electron. So as I said, to generate relativistic harmonic, we need to control the condition of interaction, so we need to control the expansion of the plasma. And for that, we need to calibrate the plasma gradient scale length. So here on the left, you can see a schematic representation of the setup that you saw just before. So you have the delayed pump probe, the solid target. In the specular direction, you have the harmonics with the XUV spectrometer and the Lanex to image the electron. And here on the bottom right, you can see the evolution of the XUV spectrum as a function of the delay, and also an evolution of the emission of the electron as a function of the delay. So what we do is we send the pre-pulse at different delay with respect to the main pulse that will give different condition of interaction, so different condition of plasma expansion, and we record the XUV spectrum at each delay. With this, we can calibrate the gradient scale length using spatial domain interferometry, and we find an optimal delay for which you have an optimal plasma expansion, so gradient scale length, for which you have an optimal generation of the relativistic harmonics that is correlated with a maximum of emission of the relativistic electron bunches. And usually that corresponds to a plasma expansion speed of about 21 nanometer per second. So once we have calibrated the expansion of the plasma and we can stand at the optimal gradient, since we have access to near single cycle and CEP control, we want to generate isolated attosecond pulse. And for the first time, we demonstrated waveform control of the plasma mirror. We sit at the optimal gradient and we vary the CEP. So here you can see a reconstructed video of the variation with CEP of the harmonics, with on top a typical angularly resolved spectrum of the harmonics, and on the left side the spatial integrated trace, and in the bottom the evolution of the spatial beam profile of the electron. And we can clearly see that it varies with CEP, oscillating between two regimes with a maximum of emission of the electron. And if we focus down a bit more on only on the harmonics, you can see that there are clear two extreme regimes offset by a CEP of pi. For the modulated regime, so the modulated trace, that corresponds to two optical cycles, so two push-pull case where you have two attosecond pulse emitted, that correspond to the modulated spectrum. And with an offset of pi, you have a continuum spectrum, which corresponds to an isolated attosecond pulse, because you only have one dominant optical cycle, hence the optimal push-pull case. And peak simulation done a few years ago in our group showed that normally we should be able to generate IAPs of 350 attosecond with an energy content of 30%, meaning a conversion efficiency of 30%, which is well beyond the gas harmonics generation process. But unfortunately, we were never able to demonstrate such value, not because of the laser, not because of the interaction, not because of the source, not because of the detector, but because of the target. So far, we were using a solid target, which is basically a big piece of glass, 2 centimeter thick, 20 centimeter in diameter, 1 or 2 kilo, that is mounted in a bulky yet precise and sophisticated positioner that rotates and translates so as to refresh the target surface for every shot at a kilohertz repetition rate. This target used to be passively interferometrically aligned so that the plane of the target stay within the relay range of our laser. And with this setup, we achieve for few rotation a deviation of the plane, so the D value of the plane of the target, of about a peak to valley of 2 micron, a bit more, which is under the relay range, and a minimized wobble of the target while it was rotating. On this target, we use 2 shots in a burst mode, which means that every acquisition, so every picture that you saw before, corresponds to a consecutive of 100 laser shots. And this is what the target looks like after hundreds of those laser shots. So all the white dots that you see correspond to laser-induced damage. And as you can see, we cannot reach the inner surface of the target because it would mean that we would have to rotate so fast to maintain the spacing of 100 micron between the spot that it would degrade the mechanical stability of the target, that would go out of the relay range of the laser and will not get a reproducible condition of interaction. At the same time, if you zoom in on those damage, you can see that we create quite big crater that creates a lot of debris, and that's actually the main drawback of the solid target, is that you blast sand into the chamber embedded into the coating of the parabola that needed to be recoated every 2 to 4 months. As I said, we have a limited mechanical stability that induces a limited amount of shots. So we have approximately 500,000 shots per phase, which is 1 month of campaign. But we have to be careful because not all the shots are useful. all the white dots that you see does not correspond to usable data of XUV, because you have to take some shots to properly overlap the beam, optimize the signal, properly realign into the spectrometer. And if you are doing a scan like the CEP scan you saw before, and you go on one circle but it's not finished, then you have to translate the target to another circle, and you might lose the signal, and you have to re-optimize again iteratively. So you can understand that it's quite cumbersome to do the data acquisition, which means that we are basically underusing the potential of our kilohertz laser. And that makes it quite challenging for regular attosecond characterization of sources, like streaking and rabbit, that usually works at high repetition rate. This is where I come in with the liquid target. So first, what is a liquid target? Well, it has been known now for many years, since the end of the Second World War, and it was actually developed to optimize the rocket engine ignition for missiles. You basically use two jets, and you create a rainfall of droplets, and you just ignite your rocket. So what would make a good liquid target in our case for relativistic harmonic generation? Well, we need an optically flat target, like the solid target. We need a sub-micron stability to stay within the relay range of our laser. That induces constraint on the fluidic mechanics, so you need a laminar flow. That induces, again, constraint on the viscosity of the liquid that you can use. It needs to be dense, because we still want to generate an overdense plasma. It needs to work under vacuum, meaning a low vapor pressure that doesn't evaporate too much under vacuum. It needs to be more compact than the solid target if possible. And also, it needs to be debris-free as much as possible. So what type of liquid can you use? Here you have a table regrouping some liquids with the main characteristic that we are looking for. And the first one that we can all think of is water. Well, it's quite good, but it freezes under vacuum, so you can't use it. Then you can think of wine or any liquid alcohol mixture. Depending on the degree of alcohol, it's quite vacuum compatible, but can be quite expensive depending on the bottle. Then you can think of the ethylene glycol, which is called PEG-1 for polyethylene glycol, one molecule of polyethylene glycol. So ethylene glycol, it's basically the antifreeze that you put in your car. So it's quite used everywhere. And it has most of the requirement that we need. As a comparison, you have the PEG 400, so 400 times the ethylene glycol molecule. It's even better, but it's really viscous. And it's not really safe in the amount of concentration that we will need. And to give you a perspective, the PEG 400 is what you have in your toothpaste to make it that viscous. In low concentration, it's harmless. But in our concentration, it's not harmless. Then you can think of other funky liquids, like metallic liquids. So mercury, gallium, cesium. Mercury is quite nice, but it's not very safe. Gallium is also nice, but very expensive, approximately $2,500 per gram. And it's not also safe. And the cesium has the tiny problem of exploding in ambient air. And then you can think of weird liquids like squalene. So it's a shark oil made from the liver of the shark, but it's quite perfect actually, and a bit better than the ethylene glycol. But I'm not sure we can provide this type of oil in Europe. So we went for the ethylene glycol. Once you know the liquid, what technology of liquid target do you want to use? Well, the first one is the one jet, so it's basically what you have under your tap. It has already been tried for relativistic harmonic generation, but never pursued. It's quite simple, but it's not flat, and it's really hard to align if you go at an oblique incident and you need to go back at specular direction. Then you have the droplet, so you make the jet vibrate, and you create droplets. It's less consuming, so you can use more expensive liquid, but the droplets are non-uniform between each other, and you can have some big synchronization issue between the laser shot and the droplet. And finally, you have the leaf technology. So you have two colliding microjets here that create a meniscus in the orthogonal plane. And it's actually quite nice because in the center of the target, you have a flat surface. It's stable, it's versatile, and you can use different liquid at the same time for any spectroscopy that you want to do. We went for the latter. When I joined the group, we started a collaboration with Enam Chaudhuri from the Ohio State University that was already working on this type of target. So here on the left, you can see a hydrodynamic simulation of the liquid target with the two microjets colliding and creating a leaf in the orthogonal plane. In the middle here, you can see what they could manage to get with the characteristic size. And if you take the middle of the center as the shooting point, and you take half the target, the time for the target to refresh, they managed to do a refreshing target of at 10 kilohertz. And the particularity of their target is here on the right, is that instead of having two jets that collide and create a target in the orthogonal plane, they have the two jets that are a little bit offset, collide in a tangential plane to allow for fine rotation of the target and to create thinner target. And this group successfully demonstrated at the time proton and electron acceleration, study of plasma instabilities, but yet no relativistic harmonics. And while I was designing the target, installing it, and fixing the issues, colleagues from Korea scooped us and successfully demonstrated relativistic harmonic generation from liquid leaf plasma mirror, but at single shot, so for one laser shot at 1 hertz or 5. And they also successfully demonstrated sub-relativistic harmonic generation at kilohertz repetition rate. So I developed our own liquid target based on the same design, but adding a 5-axis positioner to allow for total control of movement of the plasma mirror to steer the XUV beam as you would do with a conventional mirror. For the liquid, as I said, we use ethylene glycol. It's quite vacuum compatible, and it has a plasma density close to what we used to have with the fused silica target to compare. And this is the typical target that we can have with this setup. So here on top, you have the capillary holder that holds the nozzle. Here, you have the two fused silica capillary, so the end of the tubing. You have the two microjets with a typical size of 75 micron, colliding together, creating the meniscus with a dimension of 3 by 1 millimeter. And once the rim recollide, you have another target, and beneath the catcher. To push this liquid, we use two massive syringe pumps that can deliver a pressure up to 20k psi, which is equivalent to 1300 bar, with a maximum flow rate of 30 milliliters per minute, which leaves us with some room to play with some other more viscous liquid. And once it was designed, I installed it inside the chamber, but I faced some issue, the big one being the extraction. The liquid was not coming out of the chamber. So to put a bit of context, here you have the very first implementation of the liquid target inside the chamber once we remove the solid target. You have the liquid catcher. Here it's the XUV spectrometer, and here the LANX. And as you can see on the picture on the right, this is what used to be the extraction. So you have just a straight tube that goes into the chamber because our beam height is not very high. So I didn't have a lot of space, and I didn't have a lot of height for the liquid to go out under vacuum. What you have to understand is that in air, the chamber is higher on the table, and the extraction for the liquid is beneath. And in air, you have a difference of pressure, so the liquid can go out freely. But once you remove air from both sides, there is nothing to push the liquid out except gravity. And here you can see you only have 1 centimeter high column of liquid, which was not enough to push the liquid out under vacuum. For many months, I tried different solutions. First, to keep the liquid inside the target, inside the chamber to be able to shoot, or to elevate the entire setup just to see if the extraction was working. We couldn't shoot like that. But it was all failure because the catcher was overflowing. So the glycol was just accumulating, then degassing or vaporizing, creating bubble that would come out and create a fountain that would contaminate the entire chamber. We just decided to go for the big guns and actually drill the hole inside our chamber to have more column of liquid to push the liquid out with gravity under vacuum. Quite stressful, but it was a success. So here you can see a schematic representation of the interaction chamber, so the two syringe pump, the black star, the name of our interaction chamber, the liquid target, the newly hole done, and the extraction, and the turbo pumps. The extraction was working fine now under vacuum, but then other problem, vacuum issues. So the pressure was not good enough and only 10 to minus 3 millibar, which is not enough because we use high voltage detector that needs at least 10 to minus 5 millibar to work. Again, we could think of to put more turbo pumps. That's what I did. Didn't work. went against for the big guns and drill a hole inside the dome of our chamber, adding a chimney to put a reservoir in it of liquid nitrogen that acts as a cold trap and that would condensate the vapor of the ethylene glycol way faster than any turbopump could. And this way, we managed to get the pressure at 10 to minus 5 millibar, so we were good to shoot. And a bit of spoiler about the rest, but we did manage to shoot. And since this day, we shot 1 billion shots on target, which is the equivalent of 12 effective days of running the target 24/7. And now we are running into pollution issue. So the entire chamber and the focusing optic, so here the parabola, is starting to become yellow. But fortunately, it's cleanable with acetone. So we are good. And now that the target is installed, it's working, we can shoot on it, we need to characterize it to see if it's as good or better than the solid target. And since we are using microscale liquid target compared to the solid target, we need to check the thickness. So for the thickness measurement, we use white light interferometry. And if we look at the center of the target where we are shooting, we can have thicknesses that can go up to 7.5 micron down to less than 2 micron. And since we are shooting in the middle, we are shooting at a 2.4 micron central thickness, which is way thicker comparatively to the plasma gradient scale. So we are good. And the most important characteristic is, of course, the stability of the plane of the target. To do this, to measure it, we use chromatic confocal microscopy. So the principle is quite simple. You focus white light source, and you use axial chromatism. So you have blue light focusing first, red focusing at the last. You put the target in between, and depending on the wavelengths reflected of the target, you can know the distance, and you can know how that distance varies. So basically, you know how the plane of the target moves. And in the best effort case, we managed to demonstrate that for about 10 minutes, we can have a stability of less than 200 nanometer RMS with a peak-to value of 1.3 micron, which is well under the Rayleigh range of our laser, and which is way better than the solid target for such a long time continuously. So now we are good to go. So I will talk about the experimental result. First, to faithfully reproduce the result from the solid target. So remove the solid target, put the liquid target in, using the same laser at the optimal gradient for relativistic harmonic generation directly. And we successfully demonstrated relativistic harmonic generation from liquid leaf plasma mirror with here the new typical angularly resolved spectrum of the harmonics with the spatial integrated trace on top. And here you have a nice picture of what happens inside the chamber with the purple light being the plasma plume. We did notice some kilohertz shock while we shoot. So it means that at every shot, the target is opening slightly, flapping. But since the refresh rate of the target is 7 kilohertz, it refreshes 7 times faster than the laser shot arrives. So every shot sees a clean surface. So the first box to check was that we still have the plasma gradient control. We can still assess of the gradient scale length control of the plasma. On the left here, you can see a raw live video of the delay scan between the pump and the probe. And on the right, you can see the evolution of the XUV spectrum as a function of the delay, like before. But this time, we can do it live. So in the same fashion, we scan the delay between the pre-pulse and the main pulse. We record the XUV spectrum until it disappears. And we found an optimal delay for the optimal gradient, for the optimal relativistic harmonic generation. And we can sit at this gradient and just record live the signal of the harmonics for as long as we want. This time with CP unlocked. So first box, check. And the plasma expansion speed this time is 26 nanometer per second, which is comparable with the solid target. And so we have the same plasma density gradient control as the solid target. Now we need to check if we can still generate isolated attosecond pulse. We sit at the optimal gradient, CP lock and control this time. On the left, you can see the raw live signal from the camera. And on the right, you can see the analyzed signal with the typical angularly resolved spectrum and the integrated trace on top, varying with CP between the two extreme regimes of modulated and continuum. And as you can see here, we can go live between the two regimes on demand. And this time, we can generate continuous isolated attosecond pulse, again, characterized by the quasi-continuum spectrum. Of course, we are still interested in the dynamic of the relativistic electrons. So in the same fashion, we scan the delay and we record the electron beam profile. And we can see that at the optimal gradient for relativistic harmonic generation, you still have the same correlation with the maximum of emission of the electron bunch. Sitting at this gradient, we vary the CEP. And we see that we have the same correlation with the CEP dependence between the two push-pull extremes with a maximum and a minimum. So is it a success story? Well, yes. We have the same precise density control as the solid target. We have the same behavior of the relativistic high harmonics with the CEP, and we have the same correlation with the electron emission. The added bonus, we no longer need for long sequence of burst acquisition. So all the video that you saw are just 30 seconds to take, which before the reconstructed video at the beginning could take up to 4 weeks to have. So we have now a start-stop XUV source, like a light switch, and we can do some pretty cool movies. Now let's explore the new capabilities that offer the liquid target running continuously. Because now we can finally think of characterizing our attosecond pulses and our XUV source, something that was not doable before with the solid target. And that's what I did with the spectral first characterization of the spectrum. So we are at CEP unlock, optimal gradient for relativistic harmonic generation, and we just record the spectrum. So here on the left, you can see the spatial integrated trace of the harmonics as a function of time. And here you can see the evolution, so the equivalent of this. So we shot for 8 minutes continuously, generating continuous relativistic harmonic generation. And as a bit of perspective, that 8 minutes of shooting corresponds to 500,000 shots, which is an entire solid target. And studying the amplitude variation of our spectrum, we can assess of the stability of the source, and we have a stability of the spectrum of 17% RMS. And to the best of my knowledge, that corresponds to a pioneer measurement of stability at kilohertz continuously. We are not only interested in the spectral profile, but as well as the spatial profile. So instead of putting spectrometer, we have an insertable silicon plate, and we have an MCP plus phosphor screen to image the beam profile of the harmonics. And here on the right, you can see a video of the angularly resolved spatial beam profile of the XUV taken at 10 millisecond acquisition time, which means that per frame you only have 10 consecutive shots. We could do 10 millisecond acquisition time with the solid target, but we would spend more time trying to have a signal than actually getting signal. So it's another advantage of the liquid target. It's that now we can getting close to assess the shot-to-shot stability of our XUV source. And looking at the beam pointing stability, we have a beam pointing stability of 1.4 millirad RMS with a clear drift from the bottom to the top, right? And it's actually a mechanical drift from the liquid target. So again, more room for further improvement. And in terms of beam divergence, we have a beam divergence of 80 millirad full width half max that is pretty stable in time, which means that we have reproducible condition of interaction. But the last part that is the most interesting for most of people is the energy characteristic. So let me back up a bit on how do we measure usually XUV pulses. So the widely used technique is to use XUV photodiode with aluminum filter or CCD camera or photo-induced current on gold or copper plate grid. So here on the right, you can see the actual photodiode that we use to do the measurement, which is 1 centimeter by 1 centimeter, and this is the regular photodiode that most of people use. And we choose to do the XUV photodiode because it is what's widely used in gas harmonic generation. Why? Because it's first low cost, it's perfect for their spectral range. So here on the right, you can see a typical gas harmonic spectrum extending up to 80 eV. And if you look at the sensitivity of the photodiode, you can see that the photodiode captures most of the spectrum of the gas harmonics. And it's quite easy to implement due to the very low divergence of gas harmonic beam. Meaning that over even few meters, the beam is only a few millimeters up to a centimeter, and that would fit perfectly into the photodiode. In our case, it's a bit different. First, we have a spatial filtering effect. So here you have an animation of the actual evolution of the harmonic divergence decreasing with the increased order of the harmonics. And here you have the footprint of the photodiode that we use. So actually the photodiode can fully capture the harmonic 11, but as you can see, we can only capture a fraction of our beam compared to what we emit entirely. And second effect, we have a spectral filtering effect. So here on the right, you have a typical measured relativistic harmonic spectrum that we have in our lab, extending from harmonic 7 to 30 eV, 35 eV. And if you look again at the sensitivity of the photodiode, you see that we catch only the end of our spectrum and that the photodiode is mostly blind to all the harmonics that we have before, where most of the energy is. So we are only measuring a fraction of what we are actually emitting. So the setup that we use, so again, the main pulse coming in, focusing on the liquid target. In the specular direction, the harmonics, characterized with the XUV spectrometer. The silicon plate insertable to look at the spatial with the MCP and the phosphor screen assembly. And we keep that in place and put an insertable XUV photodiode to use the spatial beam as a schattography technique to position the photodiode. So here the light that you see is actually the XUV light. And what you see here is the actual photodiode that we use to center it on the beam. What did we get with that? So first, we measured only the energy on the detected spectrum by the spectrometer. And we suppose that the photodiode is centered on the XUV beam. And we managed to measure the energy of about 5 minutes at a kilohertz repetition rate, because XUV photodiodes are really fast and can capture at a kilohertz repetition rate. And we capture every 100 shots. We capture 100 shots every 3 seconds. Why 3 seconds? Because it's the time it takes for the oscilloscope to dump the data into the computer, so acquisition limitation. But even if we are only looking at 3% of the shots that we have over 5 minutes, which is 400,000 shots, we can have on average 230 nanojoule, which corresponds to a 10 to minus 4 conversion efficiency, which is comparable to the best gas harmonic sources, with only a fraction of the fraction that we are emitting. So technically, we are supposed to have way more. So now I will conclude on my work. So is it worth it to go to liquid target? Well, with it, we managed to now have a continuous source of intense isolated attosecond pulse at a kilohertz repetition rate. We can now use the full potential of our kilohertz repetition rate with manageable debris that are cleanable. We have a high diffraction limited beam quality, and we have a high source stability. Of course, there are some drawbacks, mostly the runtime of the target, which is only of 1 hour, with a downtime for refill of less than 2 minutes. And the collided jet geometry proved to be quite tricky to use and needs a lot of know-how because we saw the mechanical drift on the beam pointing. And as I said, we have some vacuum and pollution handling issue. So now a bit of perspective into the future. Why do we bother to do all of this? So here you can see a simulation of relativistic harmonic spectrum generated as a function of intensity for different normalized vector potential of lasers. For in LOA, in Salle Noire 2, we are around here. But many facilities around the world have way more laser intensity, such as at Ilai Alps in Hungary, where they are over here. And as you can see here, the harmonic spectrum is way broader than what we have in LOA. And it's quite, we do this because first, since we have more intensity, you have first more energy per pulse, in XUV pulse as well. And you have an increasing conversion efficiency with the laser intensity. So you are supposed to have even more energetic XUV pulse and peak intensity. And this is the second part of my PhD. So we co-developed with Ardop Industries and Beamline to do relativistic harmonic generation. It's comprised of 4 chambers. The first 2 are for the beam shaping of the laser with a contrast enhancement with a liquid target that I developed. The third chamber is the laser plasma interaction chamber to generate the harmonics with yet another liquid target that I developed for them. And the last chamber is to use the source. It was commissioned during my PhD, and we were the first one to demonstrate relativistic harmonic generation on this beamline with 10 to 19 watts per centimeter square. And you could say it's the same intensity as we have in LOA, so why are we doing this? Well, I agree, because we still have a limited interaction condition. So we are using the Silos 3 laser that can deliver on target 70 millijoule 8 femtosecond pulses at 1 kilohertz, but it has a big contrast issue. So here at 0, you have the main pulse, and what you have in the red circle is all the parasitic pulses and pedestal that messes up with the plasma expansion, and we cannot reach the optimal gradient to have optimal generation of the harmonics. And also, at 70 millijoule 1 kilohertz, that corresponds to 70 watts, which is a pretty powerful light bulb. And you have good thermal loading on all the mirrors across the beamlines. That's why, coming in 2026, we are going to use the laser in Umeå, Sweden, the light wave synthesizer 100, which is a laser that can deliver 450 millijoule on target, 4.3 femtosecond, CEP control at 10 hertz. So it's also a lambda-cubed laser, but at 10 hertz, with the same focusing condition as in LOA. And we can reach intensities of 10 to the 21 watt per centimeter square. No thermal loading because we are at 10 hertz, and with a much cleaner contrast. And the perspective in LOA, so the next step is to actually optimize the source. As I said, the colliding jet geometry proved to be quite tricky to use, and that is why we are going to move to chip target and using smaller pumps called high pressure liquid chromatography pumps. So a chip target, it's basically a slab of glass of the size of a USB key. With a slit in it, you put liquid through and you create a leaf with the same size as we can generate right now with colliding jet. But if you use the gas accelerated type of chip, where you have 3 channels, 2 for high pressure gas and 1 in the middle for the jet of liquid, well, the 2 jets of gas come and flatten the jet to create a liquid leaf on the orthogonal plane, and you can create targets with sizes of hundreds of microns. We already characterized and used those targets to do relativistic harmonic generation at Elias with SLAC. We can do a recirculating setup, so now with no downtime, so we have a continuous running target. And with such small target, the thickness can go to nanoscale thickness. So we could also study the relativistic harmonic generation, not only in reflection, but also in transmission. And once we optimize the source, we need to refocus the source. So that is the goal of our next 2 PhD students in our group. We who are supposed to refocus now the XUV stable source using a 2-axis parabola scheme done with a ray tracing software. And that is where, again, the liquid target proved to be an upgrade, because now we have a stable target. And if you look at the effect of the rotation of a misalignment of one of the optics on the pulse duration, well, if you only rotate by 0.3 degree, you no longer have attosecond pulse, but you go back to 7 femtoseconds. So that's not what we want. And to give a bit of an overview on the bigger picture, because we do want to go even higher in intensity to maybe reach the Schwinger limit, which is 10 to the 29 watt per centimeter square. And one scheme is to use curved plasma mirror. And how do you do this? When you need petawatt class lasers that you focus down on the expanded plasma, and such a high number of photons will create a radiation pressure that will literally curve the plasma and create a converging mirror that will focus the generated harmonic directly in front of the plasma to a distance of tens of hundreds of microns, and that would give peak intensity boost of 3 orders of magnitude. But to do this, we need a clean interaction between the petawatt pulses and the plasma. And for this, we need the petawatt to go few cycles. But how do you post-compress the petawatt to the few cycle regime? How do you measure such an intensity boost that close to the target? And can liquid target help? Well, I hope I convince you to go liquid or to go home. And with this, I want to thank my group and everyone who participated in my